I'm very happy with this lecture today given by Cynthia Dwork. And this lecture is generally funded by Dean Lei and Harry Shen. And they are not unable to come for today's lecture. And I would like to introduce Cynthia. I think many of you know her a lot more than I do. In any case, so she was a Golden McKay Professor of Computer Science at the CIS and also affiliated with Harvard Law School and the Department of Statistics. And of course, she's well known for her work on differential privacy, and which provide a strong privacy guarantee in data analysis. And actually, this differential privacy is not just a theoretical tool. It was widely used in industry, including every Apple device, this one, and also in the 2020 US Census. And she has also made very influential works in algorithmic fairness, cryptography, and distributed computing. Cynthia is a member of the US National Academy of Sciences and the US National Academy of Engineering and the American Philosophical Society, and also a fellow of American Academy of Art and Science. She received many awards, including the Gödel Prize, Axiom IEEE Kunis Prize, and the Axiom Kandilakis Theory and the Practice Award, and the RSN Mathematics Award, and the IEEE Hemming Medals. I mean, this is not all of them, but just a selection. And so let's welcome Professor Dwork. Thank you.
Thank you, HT. All right. So I'm delighted to be here. This is very new work. I've only talked about it once before. So let's hope that I've learned how to communicate it. I want to talk about risk prediction. And I'm claiming that risk prediction is the defining problem of AI. Meaning that there's a huge definitional problem associated with what we commonly call risk prediction. Risk predictors, or scoring functions, I'll use those terms interchangeably, assign numbers between 0 and 1 to individual instances. And these are usually interpreted as probabilities or likelihood. So what is the probability that it will rain tomorrow? Or what is the probability that this individual X will repay the loan? What's the probability that under a given course of treatment, this tumor will metastasize? And what's the probability that this individual person Y will commit a violent crime in the next 2 years? You have maybe intuitive senses of what these mean, but in fact, it's quite mysterious. What is the meaning of the probability of a non-repeatable event? We can't grant the loan, run history forward, see if Y repaid, rewind history, do it again, and get some kind of frequentist notion of a probability. So what do we mean by the probability of a non-repeatable event? And despite the fact that we don't know what we're talking about, these things are used all the time. So scoring functions are used. They're built using AI and machine learning. They're built using more prosaic tools. And they're often the bases for classification decisions that have life-altering consequences. Typically, they might be paired with a threshold for deciding if someone is medium risk, high risk, low risk, and so on. So what does a score of 0.7 mean for a non-repeatable event? One way of thinking about it, if you receive a score of 0.7, is that people like you, so among people like you, 70% have some positive outcome. But in that case, what is the metric for determining who is like you? That has to be specified. Another thing we don't know, is there in fact randomness in the world? Are real life probabilities all Boolean, 0, 1? Or is there in fact inherent uncertainty? And if we make a prediction, and it's not a Boolean valued prediction, we can't determine, based on the outcome, whether the prediction was right or not. If I predict something, with 3/4 probability, well, both yes and no are possible outcomes, and when we see one, we don't know whether I was right about that 3/4. So we have a scoring function or a predictor, and it's giving us numbers. How do we evaluate it? How do we say, is it a good function or is it a bad function? We don't even know what it's supposed to be doing. We haven't defined that. Now, in my view, there are sort of two indistinguishable worlds. I've drawn them here. In one world, the one on the left, the green-gold world, there is no uncertainty in what's going to happen in the future, but we, as people trying to guess what's going to happen, we don't have the information. Or maybe the information exists, but we don't have the computing power and and access to all the information that we need to determine whether the current truth, which will be realized in the future, is 0 or 1. But another possibility is that there's real inherent uncertainty. And right now, there's a probability of a half of a positive outcome and probability of a half of a negative outcome. So in one case, we as people trying to score or classify score, we have uncertainty because we just don't have access to the information or the computing power that we need. And in the other case, there's just inherent uncertainty. And these two worlds are really indistinguishable. Everything we ever see, all outcomes that we see, are after all the uncertainty has been removed. The tumor metastasized or it didn't. The person committed a felony or did not. The person will be indicted or what? Anyway, all observations, again, are of outcomes. So observations look like the green-gold world, even though the reality could be the red world. And the unresolvability axiom says that the existence or not of inherent uncertainty can't be resolved by computing on finitely many observations. And there are consequences to this. When we train a predictor, we train it based on real-life data. And real-life data looks the same whether we're in the green-gold world or in the red world. Once the observations happen, that's it. There's no uncertainty remaining. So the distribution on predictors that we will build from the training data will be independent of whether real life is arbitrary and real valued or real life is Boolean. And we can't ask that a predictor F be correct on outcomes if there's inherent uncertainty. An F that always says 0.5 is the most accurate description of reality in the red world. And we don't know whether we're in the red world or in the green-gold world. So again, how should we evaluate a scoring function? Now, this is not really a new problem. The question about evaluating prediction is quite old. In particular, it has a long history dating from the early 1980s in the online forecasting world. So think weather prediction. One desideratum is that the forecasts should be calibrated, meaning, for example, that it should rain on 70% of the days that receive a score of 70% chance of rain. In the online setting, we don't usually assume that there's any kind of a distribution on the data. And remarkably, you can have calibrated forecasters even so. In the batch setting that we're more familiar with from AI and machine learning, we assume that we have a bunch of samples drawn from some distribution, and we're trying to make predictions for draws from this distribution. And there, calibration is trivial in the batch setting. You look at your training data, you figure out what the population average is, let's say 70% again, or 80%, and then we just say 80%. And indeed, if that's the base rate, you're going to be right. You're going to be calibrated in the future. So that's clearly not satisfactory. We could say, okay, we don't like predictors that always say the same thing, so let's insist on having some variance. But that would be the wrong thing completely in the real world, where in fact everybody does have a 50-50 chance. So again, how do we evaluate our predictor? What do we want from our predictor? So I need to introduce some notation. I'm using O drawn from a Bernoulli with probability P with parameter P to mean that a Boolean outcome, O, is obtained by flipping a coin that has probability P of coming up heads. If it comes up heads, we assign a 1. If it comes up tails, we assign a 0. So Bernoulli of a half is just an outcome obtained by flipping a fair coin. Bernoulli of 0 is always 0. And Bernoulli of 1 is always 1. I'm going to use the notation pi star to be the true probability, which might be Boolean and it might not be, that I will receive a positive outcome. And I'm going to use the notation OI star, so the stars mean real life, to be a draw from the Bernoulli distribution that has probability pi star of coming up heads. So this is the real life outcome that happens to individual I. Our inspiration for addressing this problem is from pseudo-randomness. So a random sequence truly has no pattern, and its next bit is truly unpredictable. Instead, a pseudo-random sequence does have structure, but it doesn't have structure that sort of mortals can figure out. There's no discernible pattern. There's no efficient prediction mechanism. There might be an inefficient prediction mechanism, but there is no efficient one. And that's usually captured by saying that pseudo-random sequences are polynomial time indistinguishable from truly random. So pictorially, we have some efficient or polynomial time algorithm that runs in time that's polynomial in the length of its input. And it gets a string, and it's trying to guess, is this string random or pseudo-random? And if we flip a coin, a fair coin, and feed it either a pseudo-random or a truly random string, and we do this multiple times, its chance of guessing correct should be a half, or close to a half. That's what pseudo-random would ensure. And amazingly, it is possible to build pseudo-random sequence generators that have this property under certain complexity theoretic assumptions. Taking inspiration from that notion of indistinguishability, we're going to define what we call outcome indistinguishability. So now, instead of trying to determine whether a sequence is random or pseudo-random, our distinguishers are trying to determine whether an outcome OI is drawn from real life, meaning it's drawn from a Bernoulli with probability pi star of coming up heads, or instead, it's drawn according to the model of the world given by F. So we have a predictor F. It assigns to an individual I a number, F sub I, and we could draw OI from the Bernoulli distribution with parameter Fi. So either OI is coming from real life, meaning Bernoulli pi star, or it's coming from F, Bernoulli with parameter Fi. So that's what our distinguisher is trying to figure out. And we'll say that a predictor is outcome indistinguishable with respect to a distinguisher collection A if no ordinary A in the collection blue A can distinguish real-life outcomes from those drawn according to F. So just as our p-time distinguishers had probability a half of being correct in guessing whether something was random or pseudo-random, we want these to have probability a half only of being correct about whether OI comes from real life or from F. Armed with that definition, we can actually create a hierarchy of outcome indistinguishability, where the levels of the hierarchy vary according to the degree of access that the distinguisher has to the predictor F. So in the most simple form, we have what we call no access outcome indistinguishability. And our distinguisher only gets instances I and outcomes, and it doesn't know whether those outcomes are from pi star or from fi. The next level up is the one we've been talking about. Our distinguisher, it's called sample access OI, and our distinguisher gets, in addition to the instance I and the outcome OI, it gets the prediction fi. So it has strictly more information than the no access OI distinguishers do. And then you could get fancier. So for example, you could say that the distinguisher, in doing its computations, may dream up some instances j and say, tell me what the prediction is for this j. Tell me what the prediction is for this person over here and that person over there. So again, that's strictly more power because it gets to ask about the predictions for arbitrary individuals. And then yet more, the distinguisher might be just given the code for the prediction function f, and it gets to examine it and do whatever it wants. We will focus here at the second level today. So again, remember that the predictor f is outcome indistinguishable with respect to the collection blue A of distinguishers if no member of blue A can distinguish real-life outcomes from those drawn according to F. The amazing fact is that outcome indistinguishable predictors can be constructed using only real-life outcomes data. So we have our collection A of distinguishers. We get access to samples of the form I and OI star, like here's individual I, here is what happened to individual I. This is your normal notion of labeled training data. And using just those, we can construct a predictor F that is outcome indistinguishable from P star with respect to the collection A of distinguishers. And this was done technically by noting a strong connection, an equivalence relation between outcome indistinguishability at this level of the hierarchy with something called multi-calibration, which was formulated and studied by Aber, Johnson, Kim, Reingold, and Rothblum. And they have a multi-calibration algorithm that works from samples, so we get one for free by understanding the connection between these. Okay. Notice, again, and it's really important, that the algorithm for building the predictor F that is indistinguishable from P star never sees P star values. It only sees Boolean outcomes, labeled training data. Okay. All right. So this line of work, this outcome indistinguishability and so on, arose in the context of algorithmic fairness. And I would characterize this very rich and powerful vein of algorithmic fairness work as a kind of accuracy as fairness notion. But it's talking about accuracy in the real world P star. So it's a powerful framework, and it has applications that have, as it turns out, nothing to do with fairness, but it's only describing the real world. And the real world is lousy. So while outcome indistinguishability is very descriptive, it is not prescriptive in terms of what you can do for fairness. And that's what the rest of this talk is going to be about. So corrective transformations, which are ways of moving prediction from the current icky world to a better world. And this is joint work with Omer Reingold and Guy Rothblum. So imagine that we have on the right a utopia. And in the utopia, everybody is supported and helped to achieve their maximum potential and their best health and so on and so forth. So we have individuals X. What happens to real life people? They're beaten down, they're discriminated against, they have depression, they're in a world in which they don't have access to contraception and abortion. The real world is lousy, and it changes an individual X from the utopian state into some other form X prime. Similarly, one's chances of a good outcome, or whatever, given by U star of X in the utopian world, are transformed to the not-so-good real world, to this lousy real world. So X becomes kind of the distorted X prime, and U star of X turns into P star of X prime. And this transformation destroys information most likely. So I imagine that this transformation destroys information. And we can't claw our way back to utopia or predictions about what would have happened in utopia. Now, before I say what it is that we hope to do, I need to define one or two more terms. Think of your predictors, and the predictor could be real life P star or it could be some other predictor. Think of your predictor as a giant vector, a vector of dimension the size of the universe, where this is like the number of possible people in the world. So it's this giant vector where the ith element is the prediction for xi. We're interested in transformations, I'm going to call them tau, that are applied to this predictor P and give us some other predictor, which I'm calling tau of P, and I'm setting it off in square brackets so that you know that that's the name of a new predictor. So I go from the vector on the left to this other vector on the right, where now the ith element is tau of P applied to xi. And I'm thinking of tau as being something that operates on pairs. It takes an individual x and P of x, and it produces a transformed prediction. So that's actually a definitional equivalence. Tau of P applied to x is defined to be tau applied to x and P of x. Now, don't think for a minute that we get our hands on P of x. We never get our hands on Px. We don't even know whether Px is Boolean or not. But the concept is well defined anyway. If P of x exists, we can do things like add 0.1 to it or something like that. So in fact, let's look at a potential transformation. And I've chosen just some very simple ones. So first example, let's say that we have a group G and we just wish to boost the scores for members of G. We don't know what the scores are, but we want to boost them. So that would look like add 0.2 to the scores of members of G. Of course, these are supposed to be probabilities, so we have to be sure that we don't exceed 1. So formally, tau P of x will be the minimum of 1 and P of x plus 0.2 for members of G. And for people not in G, it's just P of x. So that was our first example. For the second example, I want to introduce the notion of a parameterized transformation. So the transformation can be parameterized, and in that case, it will be paired with a learner. And the learner will learn values of the parameters, the right choice for the parameters, by studying real-life outcomes data. So here we have our learner L. You can't see that. Okay, so here we have our learner L, and we feed it labeled data with real-life labels. And it sees a bunch of those, and it produces some parameters alpha. So one use of this might be to a particular way of ensuring what's called demographic parity, which would say that for members of groups, disjoint groups A and B, the probability of a positive outcome is the same if you choose randomly from A and if you choose randomly from B. And this can be done, there are many ways to do this, but this can be done by learning this factor alpha, which is obtained by computing the base rates or estimating the base rates for members of A, that's PA, and the base rate for members of B, which is PB, and then computing with those. And of course, PA and PB can be estimated from real-life training data if you have samples from A and from B. So that gives us a different transformation. At this point, it's appropriate to say, okay, fine, but where is tau coming from? And the answer is, I don't know. I mean, it's a separate question. So it's exogenous sort of for the purposes of this talk. Hopefully, our ideas of what can be done to ameliorate bad conditions will come from combinations of experts in wisdom and ethics and policy and history and geography and arithmetic and machine learning and so on and so forth. For the purposes of this talk, though, we're just going to assume that somebody has come up with tau and it has been determined or agreed that tau of P star, which I'm going to now call Q star, would be a better world than the P star world. So we don't have our hands on P star. We surely don't have our hands on Q star. But we want to ask this question. We have no data from the world of Q star. And the question that we want to ask is, can we, or when can we build a predictor, let's call it G, that is outcome indistinguishable from Q star? But we have to do this only using data from real life. So pictorially, we don't have our hands on P star, but we have samples from of the form xi oi star, where oi star is drawn with Bernoulli pi star. From this, we have seen that it's possible to create a predictor F that is outcome indistinguishable from P star. The situation on the other side, though, is worse. We have no samples from the world of Q star, no realizations. It's a world that doesn't exist. And so without having the equivalent of these samples, OI star, can we build, or when can we build, a predictor G using only this for input that is indistinguishable from Q star? We can't build Q star just as we can't actually build P star. We can build something that looks like P star with respect to the distinguishers in A. Can we build something that looks like Q star with respect to the distinguishers in A using only real-life samples? That's the question that we're studying. So it turns out there is a characterization. And in order to explain it to you, I need to define what I'm calling a random instantiation of a predictor. So remember our view of a predictor as this giant vector that is indexed by elements in our universe. Suppose now that P is not Boolean, so it may be real valued. or some of its entries may be real valued. A random instantiation of P says, flip those coins, choose an instantiation wherever you have uncertainty, and call the result P prime. So P prime of X is assigned the Bernoulli, a draw from the Bernoulli distribution that has probability P of X of coming up heads. So P prime of X is always Boolean. It's a draw from a Bernoulli. So we go from something which may not be Boolean to something which is Boolean and is a random instantiation of the non-Boolean one. There may be many possible random instantiations of P. The one case where there aren't is when P itself is already Boolean. When P itself is already Boolean, then every random instantiation, P prime, is exactly P. Nothing happens. There's no uncertainty left. Bernoulli of 0 is 0, Bernoulli of 1 is 1, always. Okay. Now, okay, I just said that. Good. So the key property turns out to be what we call robustness of the transformation to random instantiations. Intuitively, we're asking the question of whether tau of P looks like what we expect if we take a random instantiation of P and look at tau of P prime. So P prime is a random instantiation of P. What about tau of P prime? So let me explain that. On the left, I have the world of P here. So here's an individual X. P of X is this value V. And if I take a random instantiation, my first random instantiation will be either 0 or 1. I'm going to call that U1. If I take another random instantiation, then I'll have a possibly different, possibly same value U2. U3 is from a third random instantiation, and so on. And by definition, because these are draws from Bernoulli with probability V of coming up heads, the expectation of the UIs here is going to be V. Now, let's look at the other world, the world of tau of P. So under tau, maybe X is assigned a different value, V prime. For the random instantiation that gave us U1, we have tau of that random instantiation of P. Then for the random instantiation that gave us U2, we have tau of that random instantiation. I'll call it U2 prime. U3, I'm going to have tau of that. It's going to give me U3 prime and so on. And the question is whether the average of the primed values is, the U prime values is equal to V prime. So that's what if the answer is yes, then that says that tau is robust to random instantiation. And when we say robust to random instantiation, we actually mean that for all predictors P, it should be robust to random instantiations. Okay. With that example, well, with that in mind, with those definitions in mind, let's look at our two examples. So remember that our first example was to boost the scores of members of G by adding 0.2 and leave everybody else the same. So this is not robust to random instantiation. And to see why, suppose these are the members of G, and suppose that they all have probability of a half. So let's look at X. The probability that P assigns to X is 0.5. We do the random instantiations, and we get zeros and ones, about 50-50. And so on average, their value will be 0.5. But what happens with tau of P? So since X is a member of G, tau of P is 0.7. We added 0.2 to its 0.5. Let's look at the random instantiations. In this random instantiation, X was given a 1. We can't add anything to that 1. So when we look at tau of that random instantiation, we stay at 1. In this random instantiation, x was given a 0. We can add 0.2 to that, so we get a 0.2 over here. And so on. This one it was a 1, so it stays at 1. This one it was a 0, and it goes to 0.2. So what we have on the right surrounding x is a mix of 0.2s and 1s instead of 0s and 1s, and about 50-50. So the average on the right in the satellite values is 0.6, whereas the value that tau of p assigns is 0.7. So this is not robust to random instantiation. On the other hand, the demographic parity example is robust to random instantiation, and roughly speaking, this is because with high probability, a random instantiation of p will yield approximately the same values for alpha. All the random instantiations will yield approximately the same values for alpha. Amazingly, this is a complete characterization of when it is possible to build a predictor that is outcome indistinguishable from the better world Q star. So remember that if tau is parametrized, there's a learner that accompanies it. So let's let L tau be such a transformation. If it is robust to random instantiation, then there is an algorithm M for learning a predictor G that is outcome indistinguishable from tau of P with respect to any set A of sample access or no access distinguishers, so the bottom two levels of the hierarchy. On the other hand, if it is not robust to random instantiation, then there is a single no access distinguisher A so that there's no algorithm for learning a G that is outcome indistinguishable with respect to that one distinguisher from tau of P. So I'd like to try to share some of the intuition for sufficiency. So remember, we have to do our construction using only real-life samples. So we have samples of the form xi and oi star drawn from Bernoulli of p star of xi, or p star sub I. Okay. So suppose we have a whole bunch of these samples. We're going to partition them, and we're going to view them, each partition, as a collection of samples from a different random instantiation of p star. So we have these labeled data. We take our first chunk of them. We just have instances and outcomes, so maybe this came from a particular reality in which that had those matching integer values. So we can view the first collection as samples. I'm going to call it P1 as the first random instantiation of P star. Our second batch will be P2, samples from P2, which is a second random instantiation of P star, and so on. The only thing that can go wrong will be if some X appears more than once. And trust me, we can deal with that. It doesn't happen very often, and it's not going to cause real problems. So having said that, we just sort of go forward. When we have samples, now we have samples. These are samples from some random instantiation. A random instantiation is a predictor, and we have samples from this predictor. We can run our learner on this, and we can get, for the first collection, parameters pi1. For the second collection, parameters pi2, and so on and so forth. Now, our goal is to generate samples for Q star using only samples from the real world. So this is what I'm describing to you. How do we generate samples? Given a sample from the real world, a new sample from the real world, we have more than the ones that we used up here. A sample from the real world, it's an instance x and an outcome, a Boolean outcome y. And it's chosen from the real world, so y is chosen according to Bernoulli of p star of x. So given one of these, we're going to say, I'm going to assign it to one of the worlds that I've seen. How do I do that? I just choose J uniformly, and say this one. And I'm going to output xz, where z has this property. So that's going to be mysterious, so let's explain. Y is a random instantiation of p star of x. We simply define pj of x to be y. Pj is a random instantiation. All of its values are Boolean. I have a Boolean value very conveniently, it's y. So I'm just saying that pj of x is going to be defined to be y. Now I have an x and a y, and I have my parameters pi j and my transformation tau. So I just evaluate tau of pi j on xy. By definition, up here, tau of xp of x is tau of p operating on x. So this gives me tau pi j operating on pj of x. So I have my hands on a sample. xz, therefore, is a sample which is chosen from what happens when I choose a random j and I apply the jth transformation to x. Okay. All right, why is that helpful? Why is that useful? Well, by robustness, by the definition of robustness and the assumption that tau is robust to random instantiations, tau of p star on x is distributed, has the value, which is the expectation under random instantiations of what I get when I apply that random instantiation to x. So tau of that random instantiation to x. And when my number L, here I have L different copies, when my number L is large, z has expectation that's essentially the same as this right-hand side. We're just using Chernoff. So we can therefore view x comma z as a random sample from the better world of Q star. That's the intuition for necessity, for sufficiency. So I have a way of getting samples from the world of Q star. And when I have samples, I can just turn the crank of taking samples and creating something that is outcome indistinguishable with respect to the thing that I have samples from. Okay. So how about necessity? That's a much more subtle argument. And so all I'll say about it is that if tau is not robust to random instantiations, then without loss of generality, there's a large set S of elements x for which tau of p star evaluated at x is quite a bit larger than the expectation over a random instantiation p prime of tau of p prime of x. And so this is larger than epsilon for some particular epsilon. And we use that set S to create a level 1 distinguisher. So we can't even get something that is no access AI, let alone sample access OI. Okay. So this is the first work in the very rapidly expanding outcome indistinguishability multi-calibration literature that considers predictions for a better world. And we were able to obtain a complete characterization and even an algorithm for achieving outcome indistinguishability in the better world. I think the next step is to try to develop an understanding of what it is that transformations that satisfy this technical property can actually accomplish. Like, I don't really know. We have some examples, but we don't really know. We do know that we have this necessary and sufficient condition. I want to comment here that if reality is Boolean, if there is no uncertainty, then indeed all transformations are robust to random instantiations because the random instantiations don't do anything. The problem, though, is that by the unresolvability axiom, we have no idea if we are in such a world. And so we have to hedge our bets, and we have to prove that whether reality is Boolean or not, our transformation is robust to random instantiations. Okay. And the second thing that we can do is we kind of have this sort of holodeck, but we can use the technology to explore proposed transformations. Like, you can say, okay, here's an idea of how we should change things. Let's create predictors that are indistinguishable from the world that we would get by doing this, and see, what do we think of it? Do we like it? Did we see that we missed something? So we might be able to do some good forensic work that way. And that's what I've prepared.